All right, everyone, welcome to another life science session. Today with Nick and myself, Carlos, just to give you some updates and just carry on with work. There's been some interesting developments recently. We are essentially intersecting with efforts on observer theory, and we want to make sure that we get all these ideas straight, as they are still in sort of proto formal form. So I think I'm gonna jump right in to share where we left it. So in case there are any viewers that like to see where we're standing, let me share for Nick's benefit as well. I'll just share the whole screen, I guess. And if I can get rid of this, okay. So Nick, you can see this, right?
Yes.
Okay, so basically, here's what we're trying to build. So we're trying to build a dictionary, or at least our hope was that we would build a dictionary between infrageometric concepts that involve hypergraph rewriting, that involve this idea that mathematics is constructed from lower level machine like operations, and we'd like to essentially bridge over to mathematical theories that are well understood and they have a good amount of theory behind them. So in this particular case, we're looking at differential geometry, and so we summarized, we gave some reference textbook that we like to more or less follow. For those of you unfamiliar, this is a pretty good introduction to differential geometry if you want to properly study the subject. We identified some keywords that we'd like to be confident that we understand in our setting eventually. And then I drew some concept maps with our flashy hypergraph booklet that allows us to do this nice conceptual maps. Just to show that differential geometry is this unique mathematical theory that exploits specific aspects of algebra, topology, and real analysis, and generates these notions that are unique to it. Things like smooth manifolds, or directional derivatives, or the notion of a tangent functor, a curvature tensor, principal bundle, form integral. Stokes' theorem as perhaps one of the goals to attain in terms of a target goal of what to encode in infrageometry. So we began by, as you might remember, if you've been here in the live streams before, you might remember that we were a little bit stuck, and we wanted to go wide and see what options were out there in terms of encoding differential geometry into this hypergraph rewriting language. And we have some candidates, and these are all possible candidates. There are sometimes more than one candidate for the same notion, and there is many missing parts that we don't know how to encode. So one of the particular instances that caught our attention was when we were talking about maps. We were talking about charts in particular. So those will have to somehow encode the notion of mapping in mathematics, something that takes a set and assigns values to every element of the set to another set. And we don't know how to do that exactly. We are still figuring out exactly how to do that. But in the process of discussing this, we essentially came up with the possibility that observers, as we have been thinking about them in the context of observer theory or the physics project, might be very relevant here and might be the key to possibly encode a lot of these things. So what I'm going to do today is I'm going to present to you sort of a rough introduction of that idea, and hopefully Nick will have his very timely suggestions and insights, and then we'll take it from there. So yeah. Oh, hey, Evangelos, I see your comment. Kind of loud. Is that the audio levels here? Because I just actually changed the the equalizer here, so maybe that's a bit better. I don't know if you're referring to that, but I make the screen a bit bigger actually, just in case. So the other thing I want to show is this particular angle here. So let me just collapse these things for kind of presentation mode. Right. Okay, so as a quick summary to frame the conversation, and as perhaps a warm-up for those of you who are just joining us for the first time, the basic idea here is that we want to, so we have this framework where hypergraphs are being used as a general substrate for computation. So it's essentially the substance the world is made of, in some sense. And rewriting rules are the thing that infuses some life into this substance. And so we are trying to imagine what a mathematician looks like in this setting. And at the moment we are being quite high level in terms of our encoding of it. So we are not trying to do something very fundamental, like sometimes we try in observer theory, where we try and essentially define a notion of observer that is emergent from a pure sort of noisy rewriting system. Here, at least I was trying to accomplish is to have a much more focused and concrete notion of mathematical observer. So the summary of a mathematical observer in this context, which, I mean, you can think of mathematical observer essentially as an agent in the informational space that sees some form of computational phenomena. So in concrete terms, this means the following. So it means that so we're going to use hypergraphs as an informational substrate. What this means is that you should be thinking of nodes as memory. As a single node is simply a memory locus. So essentially a virtual place that has no information other than the fact that locus might be populated by some combinatorial data. And that combinatorial data is what we call edges. And we are assuming all forms of data structures like undirected edges, directed edges, many-to-many, cyclic, and everything in between, right? So that's the notion of a hypergraph that we're considering. Now, the question then basically becomes, what makes a rewrite system something that is made of the hypergraph substance and sort of made alive by some rewrite rules? What does it make? How does it become something that we recognize as mathematics, or what we would call a mathematical observer? In my opinion, there are two key ingredients to this. A first ingredient is what I would relate to or describe as attention. So the fact that when you do mathematics, your attention is somewhere, right? So you are, when you say, you write your statement in a theorem that you're trying to prove, you say, let X be a set, blah, blah, blah. That's essentially saying, I'm going to point at this thing as set X, I'm going to give it a name. So there's some degree of attention. Not only the fact that there's an object, there's a set, but there's some kind of attention. So to me, in this context, that's going to be something like hypergraphs being labeled somehow. So they carry some sort of name, which essentially allows us to distinguish pieces of combinatorial information. So in other words, not all combinatorial data is born equal. So mathematical observers actually can retain the distinction between this hypergraph corresponds to A, this hypergraph corresponds to B, although they are made of the same substance and they coexist in the same space, and sort of they are considered as the same thing, right? So perhaps I can make this a little bit bigger just for everyone's benefit. So that's the first thing. We're trying to, this is actually rather small on the live stream, so let me actually zoom in. I think it'd be better for everyone. Okay. So, so this is the first thing. And the reason why I would like to have this is that mathematics, so the other ingredient, basically, just to collapse for a second, the other ingredient is something I would call operativity, to just use some random word. So operativity means that there's a notion in which objects are being operated, right? So when you think of mathematics, take your favorite instantiation of it, be it more category theoretic, more set theoretic, more type theoretic. The one thing that is common to all these formalizations of mathematics is that there are well-defined notions of operations. Right? You have a well-defined notion. In category theory, that's kind of the foundation of the whole thing, because you begin with objects and morphisms between them, which are the abstraction of operations. In the case of set theory, you have sets and maps between sets, which or different notions of maps. So in all these situations, you have a very certain notion of operation, something that essentially amounts to a process that can terminate and that has a well-defined output, so to speak, right? So these I would call operativity in a general sense, in the sense that things can operate and have that definite sort of feel to it. And the question here is, so going back to having a labeling ability, this allows us to say, well, if I have this kind of situation where, as an observer, I am identifying object A and object B to be this particular informational structures. Now, remember, we could be doing set theory here, right? We could be saying that these are just literally unary edges on these vertices, and this just look like the enumeration of a set, of a finite set, and that's, familiar territory. But we are allowing ourselves a little bit of flexibility, and we're saying these are hypergraphs in general. And then we're going to assign some rewrite rules, which, when you think hard about them, just correspond to things that you can manipulate, things that you can somehow. These are basically interventions on your data structures, right? These are things that you can intervene in your data structure. So you say, anytime you find a pattern that looks like this is the conventional sort of composition of morphisms, if you like, but every time you have a directed edge X and a directed edge Y in this particular pattern, you rewrite something and you label it with the two names put together or whatever. And similarly here, if you have two ternary edges sharing two nodes, then you rewrite a whole quaternary edge on top of both, right? So the idea is that if I begin with this initial state, right, with BA and as this blue and green hypergraph, and I apply the rules R1 and R2, in this particular case, the system becomes confluent, because you scan all your hypergraph for possible labeled type hypergraphs that match those patterns, and then you rewrite as you encounter them. And as you rewrite them, you will get, if you ignore the non-matches, so to speak, you could draw the whole thing behind it if you want. That's just a matter of attention and labeling. That's why I think this is an important part. Then you have essentially the hypergraph version of this sort of situation, where you're saying take object A, take object B, and form the operation AB with the two of them. In this case, the object AB is just this new hypergraph that corresponds to this particular data structure. So there are two things were crucial here for us to be able to define. So note that everything that goes on here is just hypergraph rewriting. Right? There's nothing other than hypergraph rewriting, but two things are crucial. One, there's a labeling system that needs to be kept consistent, and two, the hypergraph rewriting is confluent, so that I can identify a single output hypergraph as my result, right? As my end point of my computation, what I would call the output of the operation, right? So basically, what goes into the right hand side of this equality, basically saying that product of A with B or operation of A with B goes to AB, this particular new hypergraph. Okay, so what was crucial there? Okay, so labeling is one thing. Okay, for now, labeling, I don't think it's going to be that big of a problem. We might want to go into the philosophy of why this makes sense and what exactly are labels, and what are exactly labels? Are they any just characters or like elements of a finite set that we don't really care about, or do they have any structure to them that we need to care about? But we can leave that for later. Now, the crucial point that I'm trying to make here is that what was essential in this construction was the fact that the rewriting was confluent. So that no matter how I applied the rules, which order, with whatever strategy, I was sure to find a single final state that is inert with respect to the rules, and that gives me a single hypergraph, right? So that's called confluence, and I am posing here that it might be that operativity is essentially equivalent to confluence if you set things right in a particular setting. So just to frame the question or perhaps the thought, let me tell you that there are many processes. There are many rewrite systems that look very much process-like, but that otherwise don't correspond to something that looks operational. So something that doesn't look like something like an operation that you would do in mathematics, meaning that they are not confluent. So actually, this particular flow model, so I call it flow 1-2 just because it's flow with a unary and a binary edge. That's the number code if anyone's curious. So this actually, Sam Rudke in our community has been exploring this particular system and has been dipping into our hypergraph packlet. So tomorrow we might say more about that in our community live stream. But anyway, the point is that if you have this rule and you have something like this initial state, it's clear that if we form the states graph of iterating the possible applications of this rule, you can imagine, I apply this pattern, and by the way, what these rules means, because you might be seeing two hypergraphs that are isomorphic, these things are actually tracked. So these two vertices are different. So what this thing is doing is essentially displacing the unary edge along the binary edge. That's what the rewrite rule does. So it's clearly conservative in some sense, and therefore, when applied to this initial state, you can imagine that you can look at every unary edge and say, well, this is going to be moved here, but then it can come back here or go there, or this one has two unary edges, so you can throw two in this direction or one and one, and so on. And the thing keeps evolving. So if we plot the actual state graph for just a couple of generations, you would see that there is this structure which highlights the fact that things are essentially flowing. There's a finite number of states that we can attain. It's not that this will blow up and grow forever, because the rule is conservative. I mean, the number of edges is always conserved. The multiplicities are conserved, but clearly there is no sense of what's a beginning and what's an end. I mean, you can begin somewhere, but certainly there's no notion of where you will end, because the rule will just keep applying. There is no sense in which this rule cannot apply to any of the states, right? So that's in a sense some kind of cyclic process that will never stop. So this rule with these states will just go on forever, and there's no termination. So the contrast to this is what I'm the candidates we have for what we could call mathematical observers in infrageometry. The contrast is trying to implement something like multiplicity. So this is something that James Wiles, when he was here a couple of weeks ago, he tried to guess himself, but now we can look in a bit more detail and with the actual implementation. So multiplicity, remember, is just counting the number of edges that occur at each particular location of a hypergraph. So in this case, we have a double edge on a single node that goes to a single edge. Now, same thing here, double binary edge that goes to a single binary edge, and so on. So the game here is, okay, if you give me a random hypergraph, consider this hypergraph, right? Has several edges, multi-edges in several places, and some structure. The idea is, if we apply these rules combined, they're going to are going to match where multiple edges occur at the same time, then we're going to get a graph, a states graph that looks like this. So I need to actually make it a little bit smaller so everyone can see. But this is the shape of the graph. So it's very clear. As you can imagine, before I review the whole thing, the application of this rule is clearly going to lead to a confluent system, right? Because it's going to scan for where there's multiple edges, and whenever there is a multi-edge, it's just going to rewrite it to one fewer edge on that place. So it's going to keep doing that until the final hypergraph is simple. There are no multiplicities other than 0 or 1 between any possible virtual edges. So indeed, when we plot the system, we have initially a wide range of possibilities, of course, because the rules can apply in many different ways. But eventually, we get a final state that is indeed, as you can see in the tooltip here on top of the mouse, it's a simple hypergraph. You see that there are no. When we start here, we see a hypergraph with multi-edges in several locations, like you see, like in vertex 8, 3, 4, 9, 7. There's several edges there, and when we get to the very bottom, we see that there's no longer any multi-edges. And if we check things that are in the middle at random, we find some multi-edges still, and then we keep progressing. So the point is, this looks as a rewrite system. This is just a particular kind of rule. We can identify that it is non-conservative. It is reductive in the sense that the cardinality of edges is being reduced from left-hand side to right-hand side, which was different in this case, where we have the same cardinality of edges, or the same total amount of edges on the right-hand side and the left-hand side. So it's interesting that sort of naive global pattern, it already seems to give us some hints about the kind of system that we're going to get, right? The kind of system that we get in this case is something that's just sort of cycling and going around forever, whereas the kind of system that we get when we do something reductive is precisely this confluent system. And by the way, this might bring some memories for some people that have studied rewrite systems. Many, at least in the past, rewrite systems were sometimes called reduction systems. And rewrites sometimes were called derivations or reductions. So it was implied that there was a degree of this sort of reductive nature of the rules. But anyway, I digress. So this is basically the framing. The framing is, it seems to me clearly that, and by the way, remember in our previous efforts, so I think, did I have that? Probably didn't. I might have shown you. No, I don't think I did. Well, so previously we did have this notion of giving a multi-hypergraph as a general choice of a space with a function, so general spatial hypergraph, and then projecting down to it's a skeletal hypergraph. And of course, we could just define that as a function within our system, within our Packlet. And in some sense, you could say, well, but that's actually equivalent to simply saying, take these simple rules. You will need as many rules as you have arities. So basically, consider as many as the rank of your hypergraph. Rank of a hypergraph, people usually refer to the maximum arity that you can find, the maximum non-empty arity of your hypergraph. So in this case, the maximum arity is 3, but ignoring that there's a multi-edge there that just there's not picked up by this process. This can be reduced simply by using unary and binary. So that's what allows us to say the otherwise, and we would have to invest in some kind of algorithm design to say, well, you check for every edge, check if there are equals, and then do some kind of delete duplicates, and there's some nice or efficient even way of doing this. But you could always just say, well, what is the pattern that matters to you? Well, the pattern in this case is that you have more than one edge somewhere. So spot that pattern and reduce it. Just simplify the pattern. Just make it simpler. And with that philosophy, you don't really need to care so much about an algorithm, because once you define the rules and once you give the initial state, you have the full rewrite system. And if you let it run for long enough, you will attain the terminal state, and you will have what we consider to be the output. And that hypergraph is, of course, precisely the hypergraph that follows from the application of skeletal hypergraph, this kind of function that just gives you the simple version of hypergraph. It's kind of like what in the mathematical language already is called simple graph, right? That basically given any graph gives you the simple version of it by deleting all multi-edges, right? So anyway, my point is this very much resembles a notion of a unary operation, right? In the sense that I had an object, I applied some process to it, and instead of the object just flying around state space and just, having an excursion to other states and other objects, it gives me a well-defined final object. So maybe the intermediate states are not well-defined objects, maybe they are, but the point is that even if they are, there's no sense in which they are a destination or a terminal state. Now, when there is confluence, we can say that this is a terminal state, right? So anyway, that's sort of the framing of the question, and the concept here is that if we're going to find something like so one of our goals is to try to unveil in this general setting of hypergraph rewriting and things living in very complicated combinatorial high count spaces. We want to see if we can essentially fish out the mathematics that we know with this very simple constructions, and there are several ways to do this. Of course, we have on other live streams or in a different project that you might get more exposure to in future live streams. We have studied algebraic systems with pure hypergraph rewriting as well. Again, labeling was crucial there to bring out algebraic behavior. Here we're trying to do something slightly different. We're trying to capture what usually differential geometry does. So we're trying to capture notions that have to do with the fact that our objects might be treated as space, and they might be treated as notions of curve integrations, functions, function values, local function behavior, and things like that. So my guess, and Steven's guess as well at this point, and I would like to know what Nick is thinking here, but my guess is that we should take confluence as the strongest sign of operativity in some sense, and try and build around that notion and try to maybe focus or characterize reductive rules and make sense of those, and try to investigate their properties and so on. And just to give an example of what I mean by investigate their properties or their causal structure, in some sense you could imagine, like you have this initial hypergraph here, right? If you want to know what the multiplicities are in each of the edge places, right, you might need to develop an algorithm. You might think that it's automatic, that you just have the hypergraph and you can just know as a mathematical user, so to speak, you just know that number because it's finite and you can count it. But if you really only rely on rewriting rules as your tool, and effectively all you can see is the temporal causal structure of how they apply, then I would claim that this graph over here somehow contains the information that there is 2 multiplicity count here, 3 multiplicity count over there, 2 multiplicity count over here, and 3 multiplicity count over there, and everywhere else is 0 or 1 multiplicity. So essentially, we don't see it. I pose that because these multiplicities seem to be interacting because the rules are applying all over the place, right? So it's essentially a sort of a thermal application of the rules. It's kind of a stochastic application of the rules. And first I'm going this direction, which I don't know, what did I reduce here? I think I reduced some of the double edge on between 3 and 7, right? And if I continue this way, I reduce a double edge between 9 and 4, and so on. And continue here, I reduce all the double binary edges, and that's one way. But it's essentially stochastic, it's essentially random. There's no canonical choice. That's what I mean by stochastic or random. However, the moment I reduce my domain of observation, the the causal structure becomes tighter or becomes smaller to a degree. And so, for example, if I reduce to this sub-hypergraph over here, which might be, in the between 7 and 3 or whatever, right? If I reduce to this and I consider this particular multi-hypergraph, I can apply the exact same rules, and I would get a system that looks like that, right? So now the numbers that I'm interested in is 0, 2, 1 in the nodes, and then in the binaries I have 1, 2, 3, right? In the different edge places, and I would say those numbers are somehow included in this temporal structure, in this causal structure, right? But it's difficult to fish those numbers out because they are interacting, because they are still sort of being rewritten on an equal footing on some kind of thermal basis. But if you keep zooming in and you zoom all the way into a single edge like this, right, to a single edge place, and I'm just looking at that, and it happens to have 4 copies of the same binary edge and the unary edge on a side or something, and I apply the same rules, obviously what you get is this kind of system, right? Where you have you reduce and you reduce, and you get one final edge in the end, right? So the count of the multiplicity is now directly captured by the generation steps of this re-ray system. So this is just to give a very silly, very simplistic example of encapsulating a property that we thought of as mathematical, or a quantity that observers might care about, which we did a couple of weeks ago. We thought multiplicities were going to be a very relevant way to think about functions in our setting, and all this shows is that the property of multiplicity might be directly encoded by just applying rewriting and looking at the temporal structure. Now, obviously, the crucial factor here to actually bring up something that is explicitly related to multiplicity is the domain of application. So if the domain of application is the entire hypergraph, then I get a big, complicated causal structure that, nonetheless, I believe, somehow, if properly symbolically kept, contains the information of the multiplicity there, because technically the paths where rules apply only to sub-hypergraphs are contained in here, of course, right? Because you could just only apply the rules of a certain sub-hypergraph. And this is brought out by actually just reducing to that sub-hypergraph and applying the rule exactly only to that. And then you can actually take something like the length of the temporal chain or something, and from that deduce multiplicity counts, right? So yeah, it's that simple in a way. It's that way of assigning values. Anyway, so that's kind of the perspective. That's sort of the framework that I'm thinking about. Anyway, Nick, I'd love to know your thoughts. How does this fit in your mind so far?
Well, so far this is pretty simple. Yeah.
Okay.
No, I don't know. I don't have any additional thoughts right now. If you're looking for some insights.
Right. Wait. So James correctly pointed out that our faces are not on the live stream. All right. So volume up. Okay. That's.
Well, my face was there, but I was kind of felt lonely there.
Yeah. No. Your face was, but mine wasn't. Sorry. Yeah, I think this is a better distribution. Okay, so there are two things that we can think about here. One is, okay, so for example, what I've done is essentially try to think of like the different processes that we've used so far in infrageometry, like this idea of a places graph, where we're building essentially a line graph of our hypergraph and we are labeling things. This is something that actually wanted to bring up that we probably need to. So there's some bad interaction between multi-way system and hypergraph. But anyway. So I was thinking about neighborhoods, for example. The idea that a neighborhood in our setting, so like an open set, should be something like, you have an edge, you have a vertex where edges are incident, and then you basically take, so a neighborhood around that vertex would be an edge that takes, with the labels, vertex place, edge place being kept, that takes a union of all the possible edge places around it. So I try to illustrate with a few examples. So for example, if you have this situation, so this by the way is this kind of thing. So let me just copy over. This is this kind of thing, right? So when I have a hypergraph like that, let me copy here, and then I produce the edge places like that, right? The E's and V's are the colors here. So these labels represent the fact that something is a vertex or an edge, right? In this construction of the edge place. So if you find this situation in your places graph, so this is something that that comes from this kind of construction, right? You might wonder where does the V's and E's come from? Well, they come from this particular construction, where if you're given an undirected edge, which is sort of spatial edge, then you label the actual vertices you label with a V, and then you create a new node that has an E label, right? So that's what we call a vertex place and the V's, and an edge place with an E, simply. You do the same thing for ternary, you do the same thing for higher order. And once you have that, then you can do pattern matching with the labels themselves. And all you're saying is, when you have what this left-hand side represents, in this particular rule, this left-hand side represents a vertex that has two binary edges incident on it, right? Because there are two E's and one V, right? That's kind of obvious. And the edge that you're replacing is a higher order edge that basically ingests all the edges around it, right? So it ingests the two edges that are, and it creates a higher order edge, basically saying there is a neighborhood that contains both edge places in the vicinity of V, right? So similarly, if there's a binary and a ternary, you want that this rule actually knows that there's generally the idea that there's three edge places that are adjacent in the places graph, and so on, right? Like ternary and ternary will create this higher order stuff. So notice that the patterns on the right are always a single V, and then the rest are E's. So that's kind of that's, if you think about it, that's sort of the notion of an open ball, right? You have a point, and that's where you sit, and you have sort of a neighborhood that doesn't contain the boundary, right? So you don't actually touch other points, and that's why we want to distinguish an edge place from a vertex place. So that there's that kind of distinction. And similarly, we could define closed balls or closed neighborhoods simply by defining edges between simply vertex edges, right? That would be the distinction. So basically what I did here is I tried to recover the things that we've been building. So, tangent graph is basically just the directed version of the places graph. And similarly, you can begin, I don't know why this was not matching correctly, but again, it's just homework for later, I guess. Curve integration, which you might remember, very clearly seems to be, where's that? Sorry. Very clearly seems to be coming from, if I find it, yeah, here. This idea of a path on the places graph clearly seems to be the infinitesimal or the sort of local version of something that could be a global curve that is simply described as directed edges between vertex places. So obviously the way you go from this smaller step thing, like 12 to E15 12 to 15 to E9 315 to 9 and so on, like that smaller thing, the way you go from that smaller thing to this sort of whole thing, just 12 to 8 directed edge, is by rewriting with this particular rule, right? You can just rewrite with this and it will work out. You might get something noisy in the middle, because you might get something that goes from an edge to an edge or a vertex to an edge, and that is 2 steps away or something weird. But you know that it will be a confluent system, and you know that the end result will be the integrated curve, right? So that's another construction. So the pattern that I'm seeing here that I want to bring out and I want to highlight for discussion maybe is that there seems to be a pretty strong coincidence or a pretty strong correlation between constructions that we intuitively thought they look kind of like geometry and constructions that can be recovered by confluent rewrite systems. I don't know if you agree that there's a pattern here, or like the things that we basically just drew on top of hypergraphs with like our intuition of like, oh yeah, curve looks like that, and rewrite like this for a tangent space at a vertex or whatever. Like all these constructions, clearly we define them in the analogy of hypergraph is a manifold. A manifold has a tangent bundle, therefore a hypergraph has its tangent graph or something, right? Like we wanted them to be well-defined objects from a given hypergraph. With rewriting at all, then they are a result of a confluent system, because otherwise we wouldn't have a way to specify the final single hypergraph that is the result of the operation. But thinking from a very high-level perspective, it seems curious at least to know that all these things that we did intuitively happen to be very well-defined confluent processes in hypergraphs, right? Like these look extremely uninteresting in some sense. They look very mundane and boring. Like, sure, like you replace your triangles by another triangle with arrows. Like it's not very exciting. It doesn't seem like it's doing much. But what it's clearly doing is it's creating a confluent system. And actually, it's interesting that it's creating a confluent system that is generative, right? That it's not destroying, it's not reductive, right? It's not making fewer edges, it's making more edges in a sense, but it's making edges of a symmetry type that won't enter into the pattern matching anymore. So obviously that's another sure way to get some sense of confluence, I guess. If you have an output that doesn't fit in your pattern matching of the left hand side, then you're sure to sort of never go into cycles of rewriting, right? And that's what happens in many of these. Anyway, that's kind of my thoughts. By the way, if anyone in chat has any ideas, we appreciate your thoughts. As I said, some community members have really taken it on themselves to learn the Packlet and actually experiment and run some tests and some little code experimentations, and yeah, we're very grateful for that. And tomorrow we'll talk more about that. But yeah, I mean, I'm thinking a very high level here, and just to close the final thought and maybe just move to more free-form discussion. So the last thing I wanted to bring up on stream, oops, this is unrelated. So the last thing I want to bring up is that one situation where this gets a little bit interesting and it doesn't look so mundane is in the context of charts, right? If you think of a chart that, if you think of 2 places on your hypergraph that have where rewrite rules apply, and you're thinking of those as a big space where we might make mathematical observations, but we focus on 2 overlapping sub hypergraphs of the big hypergraph. We want to make sense of something that we call a transition function or a chart transformation or a chart overlap. And the only tool that we have is rewriting, right? So basically we would like to have some kind of idea of what is the general expectation when you have this sort of situation, right? We have a hypergraph, the blue one, we have the orange one. There's some overlap between the two. That overlap here is shown in pink, and we want to think, okay, what needs to happen when the rewriting is being considered there? Like it's what defines a manifold, right? Like that's the definition of a manifold is basically, you give some set of points, and then you throw some maps from a model space to that set of points, and you demand of the maps that they are nice themselves, like they're invertible and they preserve whatever structure. And then what makes the manifold is the fact that when you have images of these maps, so you have the charts on the space overlapping, then you require that you should have some form of translation between the two, right? Like you should have some form of, what this observer interprets in this chart is equivalent to what this other observer interprets in their chart, through this transformation. And in differential geometry, this corresponds to some local diffeomorphism, some sort of local change of frame of reference, change of coordinate system locally, and things like that. So what would be the analog here? What is an analog that, I don't know, like, how does this, Nick, how does this match with your idea of an observer that you've been thinking about in, say, more like physics terms of like the discrete sort of...
Which in particular? The notion of charts? Or what?
Well, no, not the notion of charts. So the notion of charts will be some kind of application of that, but the notion of the observer in the sense of a set of rewrite rules applied to some domain and it having some specific properties.
No, in a way, yeah. Because when you have a set of rules applied, you essentially produce a causal relationship between them, between the previous rewrite action and the next one. Mm-hmm. So it kind of forms some kind of chain. I was kind of thinking when you showed that the rule for curve integration that looked like transitive closure.
It does. It is. Yeah. It is transitive closure. Yes.
Yeah. I'm kind of wondering whether there is a rule that does the reverse.
Does the reverse?
The transitive reduction case, because that's like on the causal graph would correspond to the longest distance, and essentially your interval, right?
So you mean so basically just inverting the rule, essentially, right?
It's not just inverting. It's like if you're given a graph which is not necessarily closed, can you remove the edges so that it's like there's no edge basically satisfying this transitive property, so that there's no edge when there's a longer distance to that between those vertices. If there are just 3 edges like that on the right hand side, you can remove the longer hypotenuse essentially. But if you have a longer one, the reverse of that rule would no longer work directly, right? So it's kind of more general, but maybe you can do some tricks so that you still can apply it, and effectively it's going to reduce the directed graph transitively. But but it's just a side note. I don't know.
I see. But so the idea would be to have a directed graph that is not transitive, and then that is transitive, and then you make it transitive. You make it non-transitive.
No, I make it reduced, transitively reduced, right?
Yeah.
So if you have like a chain of edges, right, connected by there is a path between vertices, but you still have like an extra edge, a longer edge, which is not necessary if you transitively reduce it because there is a path already.
Oh, I see what you mean. Yes. So you want to maximize the path distance between vertices.
Yeah. That's exactly what happens, like on a causal graph in that space-time. When you compute the distance, that's the longest path on a graph. That's your, like, essentially your proper time intervals
I see.
in a setting.
Yeah. But I don't know. Wouldn't you need a rule for each path length?
Yeah, the naively, yeah. But I was just wondering, maybe you can like maybe there's some extra edges can be added temporarily that can be removed. Maybe it's not a single rule. Essentially, some clever CA that acts on your graph and effectively reduces it. It's almost like it's not obvious that it exists. It's like some kind of consensus on the whole graph.
Right.
And maybe simple rules do exist that globally act,
Right.
have an effect similar to reduction, relative reduction.
I mean, I think we are allowed a little excursion into these kinds of questions at this point. Like, I don't mind at all if the rest of today's session is about just hypergraph rewriting as a question, right? Like, in the sense that, I mean, I haven't really, I mean, funnily enough, because I've been so focused on the specifics, I haven't really been thinking too hard about, you know, in some sense. So next week, by the way, and tomorrow we will announce it again, and we'll make some noise in our networks and so on. But we are running this we are hosting this hypermatrix workshop next week, Monday to Wednesday. I will be on site in Paris at the Center for Theoretical Physics and Statistics in Paris 1 in the Sorbonne University. but we are hosting this online as part of an institute activity. So you will see a lot of experts talk about interesting stuff. Monday will be mostly ternary algebras. Tuesday will be hypergraphs, and that's why I mentioned it. And Wednesday would be more the sort of algebraic rewrite systems sort of angle, and a sort of hypermatrix proper angle. But I'm mentioning this because on the Tuesday, we'll have Nicolas Baer present about algebraic compositional rewriting. So there is a sense in which rewrite systems compose, and you have effective compositions of rewrite rules. And I am sure that that's a big part of the story here, in the sense that all these longer, the naive longer rewrites of like a path, of a given path length, that seems like a composition of the length to path rule, right? It seems like you've applied it twice, and then you've sort of generated that motif. So what I'm thinking, when this was a long-winded way of saying, I haven't really thought too much about the question of what can you do. Like, is it known what are well-defined operations for hypergraphs in just using rewriting systems, right? Meaning, it seems to me that if you begin enumerating rewriting rules with small left-hand side and right-hand side, and you begin by taking hypergraphs of some finite size of some species, let's say just unordered hypergraphs, like our spatial hypergraphs, and just unordered rules, just rules that have some unordered pattern. I wonder if there is some meaning in the classification that a lot of rewrite rules are going to be just blunt generative. They're just going to blow up the state, whatever state you give them, they're just going to blow it up. Other rewrite rules are going to be obviously trivially inert most of the time, because if they are big in their left hand side or something, or but then some are going to be reductive, or otherwise they're going to lead to confluent processes. So there's this collection that I imagine is relatively small in all the possible rules of rewrite systems that really give you like well-defined hypergraph assignments. Right? Like, given hypergraph A, plug into this rewrite system, you get hypergraph B for sure, right? So I wonder, like, if
Carlos, did you have a chance to like read our evolution blog? It's like because what you just described like seems awfully like close to the busy beaver or something else like you basically, but instead of having a Turing machine or CA, you have a general rewriting rule and maybe some fixed initial condition, and you want rules that actually produce something but ultimately hold.
yeah,
Uh,
I didn't read that part. I actually read a good chunk of it, but
Yeah.
but I
it's
didn't.
like rewriting rule busy beavers, and we were, and maybe the similar approach, like actually trying to evolve the rules in order to reach some particular goal, can also be applied here.
For sure, I absolutely think so. Yeah, I absolutely think so. And but I'm interested now in this question of bags of rewrite rules, right? Like this is essentially what we are like. There are two things in our framework, right? Like there are bags of rewrite rules, and I say bags because really there's no sense in which one comes before the other, or like there's more of one and more of the other. Like those are things will only start to matter once you have something like stochastic application or something that you want to weight the probability that one applies or something, whatever. But just very generally, very abstractly, you have just a bag of rewrite rules, and you have possible hypergraphs that they apply to, right? And so in principle, you have like an actual universe of hypergraphs that they apply to. Say all undirected hypergraphs, just general, whatever. Finite undirected hypergraphs. So this means to me that when the moment you define a universe, especially if you're defining finite objects like all finite undirected hypergraphs, right? This is a very nice universe of hypergraphs. Up to size whatever, that's a finite set. That's just a collection of things, some kind of scatter of elements in your virtual space. And then the moment you pick a bag of rewrite rules, that defines, each of them define a multi-way system on this set of vertices, right? A multi-way graph on this set of vertices. Some of them are going to give you confluent systems on them. So they are going to define actually input-output kind of situations. So I'm curious about if there are, for example, so I wonder if there are examples like the multiplicity ones, like the multiplicity rule. What is it? Here. The multiplicity bag, which basically you just say rank n, you consider n rewrite rules, which basically just delete duplicates, right? It's the delete duplicate rewrite rules. Those are clearly always confluent, right? Because what they do is they're going to be confluent to the simple hypergraph that's projected from. So that's an example of a bag of rewrite rules that, given the correct universe, it looks like a map of hypergraphs, right? It looks like set of hypergraphs projected, so mapped into a set of hypergraphs, like well-defined, regardless of initial state. So it's like it's rewrite system, yes, when you run it, but actually it doesn't matter that it's a rewrite system because you can collapse all that and say hypergraph single output, the skeletal hypergraph, So I wonder if there is. I actually haven't read. I don't have a memory of seeing results in this direction of like people characterizing sets of bags of rewrite rules and doing some kind of taxonomy of rewriting systems in this sense. Because to me it feels pretty important what kind of things you can get in this kind of way. And similarly with...
In a sense, you can think of a bag of rules in some context as a set of equations. So in a way, when you specify a bag of rules, you essentially specify an axiomatic system. And then that's essentially just to define the theory and all kind of theorems you can derive from that axiomatic theory.
Well, but in a sense, those are your axioms, but you also need your definitions, so to speak, which will be your initial state, right?
Yeah, that's true. Yeah.
Yeah. Yeah, I'm thinking, I completely agree with that analogy, but I'm thinking of something that is a little bit higher level in this context because it's like, can you identify, there are clearly some bags of rules that absolutely have this behavior, like this multiplicity thing, which is basically just duplicate deletion. That has that behavior. Or I can think of something, basically imagine these rules, but without the labels, right? Which is basically you take any pair of edges that are incident, and you just make the whole edge that involves all the vertices, like regardless of arities, right? So I think I was calling this at some point I actually studied this thing algebraically. It turns out that these things are equivalent to commutative associative algebras. That's trivia, because as you can imagine, these are things that associate without any internal order, right? So basically, they form bags of elements. Right? This is essentially
remove the brackets. It's like a rule that removes the brackets, makes them associative. No?
Yeah, and commutative.
Yeah.
Yeah, because it basically just puts everything into a big bag. So I was calling this bag algebras, I think, just because of. So anyway, and I think this bag algebras trivially are confluent as well, right? Because I think if you take any connected hypergraph, you take this the bag of rules, and you end up with a big single edge, right? You just keep making edges bigger and bigger and bigger, and you just get one final edge that is like big. It has a single high arity edge, right?
Yeah. Mm-hmm.
So anyway, there are some trivial examples. It's clear that some of these examples are, regardless of initial state, you're always going to end up in a well-defined target hypergraph. So they clearly define maps from hypergraphs to like mathematical maps, in the sense of you would have a set of possible initial states, which are all possible initial states, and you would map them to, for each of them, a single target hypergraph. So that to me seems like an interesting thing to consider in general, because like what are the alternatives really? Like you could find, I guess, orbits of rewriting orbits in your space where you have like systems that have attractors. So you end up on a finite subset of hypergraphs, and your rewrite rules only orbit that subset eventually. I mean, I guess I think that's well defined, right? Like you could have states that eventually kind of like get attracted to an attractor, and once they are in the attractor, there is no sense of like everything is reversible within the attractor. Like, all the states can be reached from flowing with the others. Like, I don't know if that picture doesn't make sense, but
well, I describe them as some kind of a rule that basically some cycles your states around, right?
Yeah. But it's possible that you only reach cycles somewhere down the rewriting, right? Like you begin, like,
I remember that example in the Wolfram physics, that example of Wolfram model is just a small loop going around some long sequence of edges, and it produces like a uniform two-dimensional causal graph. So it's like, even like cycling systems essentially produce a space-time that is infinite, and it's very uniform, so it's like a background.
Wait, so are you showing, or should I show it on the... Just maybe send me a link and I'll put it on the screen.
Oh, I need to find it. Hold on. It's somewhere in the Wolfram physics, maybe what is it? Visual Registry of Notable Universes.
Yeah.
Somewhere there, I remember. An example. Or maybe somewhere in the actual book. There was that example. It would be easier to find it there.
Do you remember if the Wolfram this Wolfram universe is considered unary edges?
Well, it could, yeah. Just
It could.
take there were a lot of examples that
Yeah.
produced something interesting with them. Emergent behavior.
So many loops.
I think I found it. Here's the link. Page 427.
Okay.
It's an example of a particle, right? So that just goes around on a loop. So it's kind of like.
Wait, what am I looking
Like
at?
your hypergraph is just cycles, because you just particle going around on this tiny loop. But in a way, it produces some space-time of the same size, but I don't know. This is one of the nice examples that minimally show some physics of particles. Just some perturbation of your hypergraph going around, and you can also see the perturbation of the causal graph too.
I see that. Yeah. This is nice. But here, how do we know that's a particle? We just know because it's some kind of
Some
some kind of motif.
By its effect.
It's basically a motif, right? That
We're supposed to be looking at the causal graph, and there you can see that it's actually curving locally your space-time. If you compare it to the background, so you have effectively have some background space-time, but particle is just traveling through it, introducing some kind of tangle in the space-time.
I'm not sure I understand, because what if my initial state is just like the circle hypergraph?
Well, that rule would no longer apply then.
So it will be inert.
Yeah.
So then there will be no causal graph, right?
In a way, yeah.
So interpretation is a little bit tenuous, right? Like it's not.
Well, background doesn't evolve. Maybe you can imagine that there's always an identity rule acting on space-time.
But will the background then look like that causal graph? Without the kink?
I think so, because you have like just an identity rule acting on all possible space-time positions, and because your space, which is the hypergraph, has some form, you only have finite places to apply it to. So at least it's gonna be similar.
Oh, but I guess there are many Okay, I think I understand what you mean, because there are many identity rules, right?
Well, it's maybe the single identity rule, but you can apply it in different places. Identity is just like one single edge identity. Go from one, just rewrite edge to an edge.
Sure. Okay. Yeah. No, but this connects to another question that we talked about a few months ago in the Jonathan era, with about dynamics, right? This analogy of rewriting as dynamics, which is pretty much this example, right?
Yeah.
Yeah, and you can assume, given the identity you rewrite, which I get, if you have identity, so in the states graph, if you have the identity rewrite rule, you have as many in the first generation. In the first step, you have as many new states as there are edges in your hypergraph, right?
Mm-hmm.
So, but maybe that's what you want? And that's pretty much what we are seeing here, right? In some sense. Like the background.
Yeah, just your space. Like not evolving with time without any changes. That's the program.
Yeah. But I'm confused. Because wouldn't the causal graph look like one state, many arrows, one state, many arrows, one state? One event, many arrows. Oh, wait.
Well, you have like your space in a circle, right?
Sure.
You can apply your identity rule to any edge. So
Yep.
you can apply like if a circle like of size 10 edges, right? You can apply 10 events, space like separated events, so they can act independently.
Yeah.
So your causal graph starts as just this like 10 space like separated events, right? Now you apply them again. Well, you have to at least mix them together. So maybe your event has to touch two edges. Otherwise, it's going to be like this 10 lines going through independently, right? Because you never mix them together.
But that's what I mean. But that's what the identity does, right? That was my
Yeah, maybe it's like an identity that involves two edges. So it kind of swaps them around, but so that the causal relationship still applies. So that they can, if you track the causality, it still can affect. Like the event that rewrites other edge.
Yeah. Yeah, but that's what I meant, that you need several identities. Like there are several possibilities of what you mean by identity. Because if you
I think like in this case, just to get this background, you just need like this one that maybe doesn't have to identity, just swap the edges. If those edges have some UID, some im assigned to them, the actual vertex name, you just swap them. So,
seems a bit hacky, but okay. Okay. Yeah, but anyway, I think this is yeah, I'm not sure. Because this feels more like discrete dynamics than hypergraph rewriting in a way. I guess you didn't find any models where you had like a kind of a package traveling somehow, like in a grid hypergraph.
Sure.
Did you find some like that?
Well, it's like a tangle. Like the same book has some, I think, has this example. Well, it's explain how the particle can look. Like, and if you have a grid and you introduce a tangle and so on, you can simply imagine this tangle actually just jumping around, right? Just on the same page. Yeah.
Yeah.
Scroll up. Yeah, but this is like essentially a grid with some identifiable pattern that you can rule that your rule can have on the left hand side, and you just can move it.
Yeah, I'm now thinking of something a little bit more sophisticated in a sense, in the sense that what's really happening there is that you are finding motifs of the same model hypergraph, and you're saying, well, this was an embedding of this motif here, and then suddenly I have an embedding of this motif over there after some rewrites, and maybe in the extreme case after every rewrite, right? Like that's maybe the extreme case that is being shown here, where every single rewrite application produces a new instance of a motif in your hypergraph, right?
What are you getting?
What I'm trying to say is that what you're identifying is, like, to say that there's something like a particle or something is moving, right? Essentially what you're detecting is non-equal embeddings of the same motif, right?
What do you mean not equal?
In the sense that they are clearly isomorphic, right? So I don't know if I'm seeing these things right, but all these states are isomorphic, right?
Well, maybe this particular case, yeah.
Yeah. I'm just taking
background.
I understand, but it needs to make sense even in the simple case, right? So even in the simple case, you have this motif that, like, from a hypergraph point of view, you can distinguish these different states, right? These will all be equivalents to the same state, because it's a right. But anyway, the point is that when I say non-equal, is that if you are really keeping track of the identity of the vertices, right, then each of those hypergraph contains a different sub-hypergraph of the same model hypergraph, which is the kink, right?
Yeah.
So my point is that motion is being detected there in an abstract sense, right? Motion is being detected because you are spotting two or more ways of doing an embedding of the same motif, right? And maybe you even have some notion of these are overlapping motifs in whatever. That's why you call it motion and not just like a scatter of motifs. But at formal level, like, I'm trying to characterize what's happening here in order to extract something, in order to generalize something, right? What I see happening is that the king is a motif. Because I'm trying to go beyond sort of the typical Stephen level observation. It's like that clearly looks like a particle moving. It's like I see that. I know that's a good pointer, but I want to go beyond that. I want to try to characterize what's happening here in some more sophisticated way. I don't want to overcomplicate it. I just want to understand what's really going on here. It seems to me that that's the case, right? Like you have a motif, and that's the thing that is preserved. The fact that these are isomorphic hypergraphs notwithstanding, like the background could actually change a lot, as you say, that's fine. But if the background does change a lot, then even more to the point, what you really do have are different embeddings of the same motif, right? Like there's not even a good there's not even a good notion of proximity. I mean, the proximity needs to be defined in the causal graph, I guess.
Yeah, well, yes. That was my kind of. Well, the observer would perceive the proximity only using the causal graph.
Exactly.
So the hypergraph distance kind of doesn't make sense
Correct.
to prescribe any distance. Yes.
I think we are in the same camp here. We're both voting for the same representative in the hypergraph parliament.
Yeah. Because like causal graph is the space-time. It's like how it was generated, whether it's like just tiny loop changing on the same isomorphic hypergraph. Doesn't matter.
Yeah. No, that's clear. That's clear. I was trying to, yeah. Okay. But then I wonder. Okay, but let's rewind it for a moment. So this was you were bringing this up because we were discussing the possibility of like cycles, or when your rewrite rules get into some kind of attractor and just go in a cycle, just keep rewriting.
Here you essentially like your multi-way system is just one vertex because it's if they're all of them isomorphic.
Yeah. No, I understand. But what I mean is that more generally, you could have something that looks more like this, right? Like this kind of thing, right?
Yeah.
But it might be that like there's whatever. I mean, this happened to be all reversible because of the nature of this. So it's a moot point because actually these are all reversible, like whatever arrows you find here. But it might be that you find like your rewrite system begins in a way that takes you to a region that looks like this, but you can't fly back, right? Like you sort of flow in the DAG, not DAG, but in the directed graph of the multi-way system. You actually begin in a DAG area, and then you land into a cycle area, right? Where you have this kind of stuff, where you have many sort of like cyclic things.
Yeah.
Yeah. And I guess for some reason I'm struggling to think of examples of terminating but not confluent rewrite systems. But maybe I'm just slow I'm short in imagination.
You mean systems that just have like multiple outputs?
Yeah.
Essentially.
Yeah, multiple terminal states.
It depends on well, we can simply make one. It depends on your rules.
Yeah, I guess you can always make something that, depending on which order or which location you apply the rule, that you're going to go somewhere or somewhere else.
Yeah. Or you can just have two different rules that produce different results. It's like, right? You can have one goes to 2 and one goes to 3. Okay, apply it to 1. There you go. Confident and
Sure. Yeah. No, that's pretty easy. No, I guess what I was struggling to see was with a single rewrite rule. That's why I was struggling. But it might still be possible, right?
Yeah, probably. Just depend on the order. Yes.
I think it might depend on the order where it's applied. But yeah, anyway, one of my thoughts for this was that we might want to think of, I don't know if this means anything to you, but like I was potentially thinking that imagine, I mean, this is not the case because this is actually bigger, but imagine that I take this, right? And how many are there? There's like 3 unary edges, which can be everywhere in 4 places. So that's like 4 times 3, 12, I don't know. There's a few dozen possible states here. Like, I don't know, some 50 states or something that this can attain, right? Like different distributions of unary edges here, whatever it is.
Mhm.
The states graph of this rewrite system is the is that right? The fully connected graph of those, right? Is that true? I guess not. No. It's not fully connected because if you have a stack of 3, or even a stack of 2 unary edges in one vertex, you cannot go with a single step to that vertex being unpopulated. You need to first move one and then move another, right?
Yeah.
But anyway, my point, that's besides the point. My point is that you have a connected, directed graph of all those states, right? And not only connected, but it's essentially an undirected graph. It's a double directed graph because if you can go for,
Yeah.
it's reversible. Is that what people use? Reversible directed graph?
Perhaps.
Let me just double check.
No, I'm not sure. Well, just undirected.
But it's not undirected. I mean, it's just doubly directed,
Oh.
right?
Well, yeah, it's directed, but well, if you have an arrow back and forth, basically usually is replaced by an indirect edge.
Yeah, I think that's just wrong. I understand why we do that, and it's fine. But in our work, that's just like a mistake because it kind of undermines a lot of the things that we're doing. Because 2 directed connections between two vertices is quite a different thing informationally in our framework than an undirected single connection, right? Like those are pretty important distinctions. Anyway,
Okay.
I'm not. I'm seeing mathematics text change. Let's see if they're responsive. Blah blah blah. Reasoning blah blah. Yeah, probably reversible is a good name because people talk about reversing or transposing a graph, whatever. Because I guess the adjacency matrix is related by the transpose. So yeah. Anyway. So. Okay. So what I was trying to say is that once you define your rewrite rules and some initial state, that generates this final graph of the finite multi-way graph of that rewrite system. And I was thinking of using, and obviously it contains all the causal information you like and all the branchal properties and all that stuff. It's contained there, right? So I was somehow imagining that we could use that as a symbolic quantity in a way, right?
The whole causal graph, or
The whole rewriting graph, not just the causal. I mean, in principle, let's possibly just think of the causal graph if you want. Like simply
like each event only records like a diff. You only know how locally the state changes, so we can reconstruct everything from just the events and their information about what the rewrite was. Right?
Well, I'm saying something even simpler. Like just take the causal graph itself and
Just
label
the
it.
relations.
Hmm?
Just the relations with no like event structure at all. Okay.
Yeah. I mean, just for an example, I don't know if we want the whole thing, but what I was thinking is that maybe we can use that whole thing, which is finite. That's the point, right? Like it's finite for a lot of rules, not for all rules. Some rules are just, indefinitely growing. But there are some rules for which it is finite. And I was thinking of using that thing as a symbolic entity. So basically, you have that and you can operate with it. You just have that as a whatever active variable. It's like, I don't know.
Like another rule, essentially.
Like another rule. I don't know, but just as a, because to me that's like I'm trying to think what a mathematical object is in this setting. Like what a hypergraph that is being observed by rules, to me, is that graph, right? That's the whole information. I don't lose any information if I say, well, just keep the whole graph. Like in this case, this one, or in this case, like this thing, right? Like just keep the whole graph. Keep that information with you, and then you can maybe think of an algebra of these things, and that's what mathematical observers talk about. Like clearly, if you go small enough, this is what we do in practice, right? Because the algebra, if you go small enough with this particular example, you would be at the edge level, kind of at the edge place level, and then the causal information of your whole graph is essentially its length, and that length is the multiplicity of that edge place. So the algebra of these things is basically the local multiplicities. It's just that's so it's some kind of arithmetic of local multiplicities, right? So
are you talking like essentially of this multi-way system graph and its algebra, or its dual, which would be the multi-way causal graph?
Well, I'm thinking, once I have this states graph, I have the causal graph as well, right? Isn't that right?
No, I don't think just the relations is enough.
You need the, I see, you need the events.
So the edges here are the events, right? But
yeah,
just the structure of this graph alone doesn't tell you whether those edges are causally related or not.
No, sorry, I remember, yes, sorry. That might be what I was missing all this time. I kind of tunnel vision into this and stop thinking about the actual, because this is what we discussed a few weeks ago, right? Where we're thinking about, we're thinking of what it means to rewrite something. What is an event exactly? Right. So let me see in this case. So if I have, let's see if I think I have to run things. I don't think I have to run things. Give me a sec. Just this. Yep. Actually. So how can I see in this one? I can just do causal graph.
Well, I think even the state graph, if I remember correctly, the edges are tagged with all the information about the event. So if you ask for edge tags of that graph, but causal graph would also do, yes. That can basically make a graph out of events.
Okay.
Maybe not.
But
maybe evolution graph was or just graph. I don't remember. Maybe states graph removes that information.
So what is evolution graph?
I think it's kind of should be the same thing as the states graph. There's some subtlety, I don't remember what it is.
Yeah, but I guess we wanted to see this. Oh, okay.
Of the edges. Yeah.
Oh, actually, I know what's happening. The edge tags might be working because this is a bit hacky. This was here. It was hidden for presentation. Oops, what's happening? Nope.
Well, if you try just edge list. Maybe edge tags is it even a function?
Edge list.
You just try edge list because that's a graph.
Well, it's gonna be long.
Yeah, it's like the giant vertices. They don't even. I think there's some. Should be a tag.
Still going.
We should have tried like a smaller graph. Why do you need this whole confident thing?
Well, I don't really have a smaller one. I have this one, I guess. Wait. And this one, for example, right? So, yeah.
Maybe just take a few. Maybe it tries to render.
Yeah, that's fine.
Well, but there's no tag. So there should be like either just graph or evolution graph should have a tag.
Oh, this was states graph, so it should do evolution graph, right?
Just graph, right? I think the graph definitely should.
Graph. There you go.
Yeah. Oh, there's like this iconized object. It's just for our hypergraphs. It actually just copies whatever when you apply our rule to the hypergraph. And it just copies all that information to that iconized object. So that much over there contains all the information. But besides that, you already have what's like minimally what edges goes as input, as an output, the rule index. Where's the other two rules?
Yeah.
Yeah.
So, okay, but what if I do cut?
It's gonna be like
Yeah, it's taking its time.
I wonder whether it's rendering of the bunch of hyper edges with enough for each event.
Probably.
Shouldn't be much longer as the actual graph generation.
Yeah, but okay, so in the meantime, this is the evolution events graph, right? So this is the one that, and that's why you have that's why you have the multi edges, right? Because they're effectively recording all the possible pattern matchings, right?
Yeah, exactly.
And then, the causal graph is a relation between the events themselves. Okay, so I understood this at one point. And these are just both superimposed, right?
Yeah, basically just turn it into this bipartite graph.
Yeah.
So it's the same as labeling each of the edges in the states graph with an event, and also like adding more edges between them.
Okay. So let me understand again. ABA is my initial state. Oh, okay, I see, I understand this. Both applications lead to the same thing. So that's why you have two events and one state. That makes sense. And then, let's see, this application affects the leftmost A, which came from being produced by this rule. And I guess that's why...
Yeah, there's a causal link between them.
There's a causal link between them. And now what is this link here? Oh, A. And that A came from here. Oh, I see. Okay, I just reloaded in memory. I have good memory, but it's slow access. I reloaded from our previous conversation that we were discussing what it meant to have this kind of causal link in hypergraph rewriting, in our hypergraph rewriting, in the new one, right?
Yeah.
Because there was some ambiguity there, wasn't there? Or some choice.
It was the same kind of choice here.
Well, in a string...
Well, in the multi-computation packet, I'm trying to be more explicit about the branches and all the ambiguities that can happen. So there is a bit more information about when the ambiguity happens, you actually mark it with additional tree position. You can think of the multi-way system as it's not a graph; it's like a tree initially, right? Before you merge any equivalent states.
Sure.
Yeah. So you essentially that's what I'm doing, just to be more precise about what's happening. I actually making this tree. That's why it's so slow, right? But you kind of record all the edges and where these edges are in this tree, and then I merge them potentially, and that's how you have multiple edges. But you still record all the events, even though they acting on the same state, but they are technically acting in a different branch of the same state, because you haven't merged them before you produce this event.
Interesting. Yeah, it's almost like thinking that any future, like equivalencing by some notion of equality or isomorphism, it's always going to carry some non-trivial operation, right? It's like, it's not, right? Because there may be rules that like add vertices and things like that, and kind of change the look of the context. So I guess the code right now just keeps track of everything at the level of, they have names and they can be duplicated, but they are actually stored in different memory places, right? Like, even though they're called the same or something.
It's not made for efficiency, but for this clearance about.
Yeah. Of course. Yeah. I'm talking about, yeah. So, but actually, this is one of the few places I think where it actually matters what you do, like at the code, like in terms of implementation, and what we mean more mathematically or conceptually somehow. Because I mean, if you write, it's the thing that I always go back to this at some point, with some regularities, like my attractor, when talking about these topics. It's like in Mathematica, if I write something that looks like this, whatever. Let's get rid of this.
I'm still running. This causal graph just can be rendered, whatever is going on. Can you try one step just for?
Oops, it's crashing.
Oh, because it actually started putting it into front end. Maybe some giant number of icons.
Yeah.
It's like every edge there has two hypergraphs.
Yeah.
Highlighted. And there's doesn't seem too many. Well.
Okay, anyway, I'll say what I was just going to illustrate by typing on the language, but you understand. So every time you write, list A, comma A, right?
Right.
That to us is like, oh yeah, it's two copies of the same thing, but really, like the language is keeping A and something else, like A in this location and A in this location, right? And
they can share the reference for efficiency. It's like if you know that it's the same, and in fact, there's some language that like James posted about it, like it's got some hype recently. This HVM and band language, they managed to make this notion of copying and duplicating things and how it reduce your terms in the language more efficient, right? So
I'm not concerned with efficiency at all. Hey memes, welcome to the stream. We're just philosophizing about the nature of lists, I guess. No, but what I mean is that it is relevant. Like, I guess when you're building your tree in Mathematica, right? Like in the actual code, you're effectively it's some expression, right?
Yeah.
So by the way Mathematica works, you can just put expressions next to each other in a list, and even though they are copies, they are.
If you have a symbol that has some giant expression and then you make a pair of those symbols, right? It doesn't mean that it gets duplicated. You just share the reference twice. So.
Yeah. So my point is, I mean, what am I trying to say? I was forming a thought. Let me go back to it. What I was trying to say is that whenever you have a state and you apply rewrites to it, like there is some degree of separateness or independence, or I don't know how to call it, or branching of the future timelines that happens every time you apply a rewrite, like in principle, right? It could be that every time you apply a rewrite, in every what you would call an event in the multi-way graph, right? Every event might produce a hypergraph that just does not speak to the original hypergraph at all, right? Obviously, that doesn't seem very useful, but in principle, you could imagine that. It's just like initial hypergraph, several matches, several outputs, and those are now new disembodied new states and on which you can maybe perform the same rule, but who cares, right?
Those are like many worlds. They don't interact.
Exactly.
But maybe potentially they should, as quantum theory tells us.
Right.
There's some interference effects, and so that has to be explained. But that's like besides the point.
No. But I think no. I don't think that's besides the point. I think that's exactly because I mean you could take that as your ground truth. Like you could take some kind of many worlds. Let's call it many worlds, right? That particular perspective. It's like you could take that many worlds point of view, and basically elaborate on it by equivalencing in a certain way. Because if your objects all have like all your reachable states are amenable to some common computing, some common comparing that you processing that you can do sort of how to say maybe horizontally. I guess that's what I want to say, right? Vertically is evolving with the rules, and horizontally is just looking at the states that are being generated. So like horizontally, you can do something with them, right?
Because like a branchal graph, but that's what branchal space, like Steven would call it, this horizontal relationship between states.
Yeah, but sure, but in order to construct the causal graph. By the way, how do I kill this now? It's completely. The not responding message is not responding. Cool. So anyway, how, like, in order to define the causal graph, right, that is connecting events, your events are based on, the causal link is based on horizontal properties, basically. Like, obviously, it comes from the vertical application of the rule, but it's based on horizontal properties of where some sub-pattern of your term came from, right?
Yeah, in a way, yeah. So that's how multi-computation packet is working. It's like you turn it into hypergraph, essentially for this purpose, in order to distinguish more easily these horizontal properties.
Yeah.
Because they just actually correspond to some extra vertex that you add.
What you mean? What I mean? So I meant to say two things. So one is that there's clearly some freedom in how to define those dependencies, right?
Yes. Yep.
Right.
Yep.
So that's one thing, and the other thing I wanted to say is that no, maybe that's the only thing I want to say in the sense that that's the core. Saying that there's several ways to do it means that. So that's, by the way, why I was trying to abstract the kink case, because if I have an initial state and I rewrite it, I need to do some kind of relation between those two things. Okay, now I'm getting the point. So if I actually show something that's meaningful to our viewers, at least, and I put this thing back on, like, okay, I can understand that the way you're building. Okay, I understand what this graph is showing now. Okay, because I see, right. So it's basically that kink over there is basically tracking the fact that every time, like, there is some dependent terms that are next to each other. So this is actually based on overlapping motifs on the hypergraph at every step, like naturally.
Mm-hmm.
Right? Like same as this thing, right? Like same as the fact that this A came from that A in this motif.
Yeah.
Right. So, right. Okay. Yeah. Okay, give me a sec. Okay, but I think this is a pretty good thing to understand. In general terms, give me a second. Not quite sure.
Well,
No, I'm just trying to think.
no, maybe next time then.
Yeah.
We'll figure it out.
Yeah. No. This is good enough for a recap and a work session for sure. But just to have some final points. Do you think it makes sense to have, like, there are several choices, but it feels to me that
No, maybe not several. Maybe there's like always some unique way of doing it right. Because the point
That's what
of
I-
making causal links right is just it's basically defining parallelism explicitly, like what events we can just rewrite in parallel, independently. So that's the only criteria to determine whether the events causally linked or not. Also, they are space-time separated or time-like separated, so whether they can be performed in parallel or not.
Right. But even that question of can they be performed in parallel seems like,
Ambiguous?
yeah, it seems a little bit like it implies some sort of like memory state that you cannot access the next thing until you actually do it, or some kind of thing. It's like,
Well, if you have a position, explicit position on a hypergraph, then you can define what it means to apply in parallel. But of course, you can, in principle, imagine that even they apply in the same position so that they overlap, but ultimately commute, then, well, in principle, it's not reducible, right? You can't really determine whether they gonna produce the same state anyway, even though maybe they do. in one particular case. So maybe there's some, in special cases, there are some tricks in order to even overlapping events somehow separate and apply them in parallel somehow. Because they commute in a way, it doesn't matter in which order you then apply them. Maybe you can, it depends. But when you at least have a position of a hyperreach or something, then you can define exactly what it means. That's what it means.
Okay. So I think we converge on the same thought in a pretty random way. Let me see if you think this addresses what you're saying. Would it make sense, or would it simplify to think that vertices on which the hypergraphs are defined are somehow pre-existing, and these are like, populated or unpopulated, but they're all there with unique IDs, so to speak, right?
Yeah.
And then you populate those vertices with, and of course, think of my no loops hypergraphs, that if you want loops, then you will kind of label something or whatever. But in that setting, wouldn't that effectively give you a direct way to answer this kind of ambiguity? This is what I'm just understanding as your position in your hypergraph. Like you're saying, imagine you have a position. Like I can only imagine.
Position in my case, well, if you just two ways to rewrite your hypergraph.
Yeah.
Because your rules apply to hyperedges ultimately, right?
Sure.
As soon as they apply to the same hyperedge, that means they overlap. So the position, in my sense, belongs to a hypergraph, to a hyperedge. Like each individual hyperedge is the position.
Yeah, but I know, but I think you're implicitly assuming what I just said, because if you have two hyperedges that are structurally indistinguishable, meaning that under isomorphism they can't be distinguished.
Yeah.
For a hypergraph, then technically what your position is not a position within a hypergraph, which might be ambiguous because of if you only really have the data of a hypergraph, you actually need the address of that hyperedge, not just
exactly. Yeah, that's why there's a linked hypergraphs there in the multi-computation.
Okay.
The link, what I call link there is that particular address, and I use it explicitly to track the quality.
Okay, interesting. Okay, so that's interesting because that has been at the back of my mind simply as kind of a conceptual point. It's like, oh yeah, maybe we need just to think about how this actually happens. But this seems to me quite important. Like it is. I mean, it's almost like we were scratching the surface and then realizing that there's nothing stable underneath. Like all this stuff needs to be somehow. Like I'm mostly speaking personally. I like when I was thinking of hypergraphs, I was just thinking of abstract hypergraphs, and I was not really, in a sense, I was assuming that they were backlit hypergraphs, like something I would be able to operate on the backlit, right? But the backlit does assume this sort of idea of vertices being this kind of memory addresses kind of thing, where you can populate or not, but effectively they are pre-existing. And in terms of the algorithm or the criterion to know when two things are overlapping, if you have like a sea of pre-existing nodes, of pre-existing vertices, the kind of virtual vertices maybe, if you want to call them, or something, but they are pre-existing, unique, and fixed. That's the common thread through all the rewriting that happens, right? Because things happen on the same set of vertices with the same addresses, right?
Yeah, and unless there are some new vertices introduced. And
yeah, but then you just select an empty one, right? And you just populate that one, right?
Yeah, well, it's just you assign a new ID to it.
Sure.
Yes. Sure.
Yeah. But which is in the picture I have. I mean, it's just to like have a visual correlation to it. It's like I imagine this kind of like grid or like pool of vertices just floating around, or like, you know, and they all have unique identities. It's like the atoms in a chemical solution, right? They are indistinguishable but unique, right? And different in some sense, right?
Well, it's the only property to be distinct.
Yeah, exactly.
Yeah.
Exactly. But I mean, they might carry other properties, but you know, chemically, the properties are emergent on the compositions they form, like the molecules and the bonds and things like that. And that's very much how I'm thinking of hypergraph. Right? Like you have these things that are floating around, and you just need to know that they are distinct. But you don't need to order them in lists. You don't need to assume any kind of internal structure to that thing. It's just a big sort of, everyone is equally different to each other. And yeah, I think that, but then the what I was trying to get at is, doesn't that resolve more or less uniquely when to assign the dependence? Because you can always look at the actual address, right? Or is there still ambiguity there? Or
No, I don't think so.
Okay, yeah, that's good. That's what I thought. That's okay. Okay. Yeah, I think this is giving me enough to go on off. So let me see if there's anything in the chat. Oh, memes is asking something. Were we interpreting places where the graph becomes disconnected as black holes? Perhaps this is a different context. Yeah, I don't think. No, we were not in the context of interpreting physics. Yeah, name, address, and so on. Yeah, it kind of is. Interesting. So it means just dropping some hard facts. 4 dimensions is the unique dimension with a countably infinite number of tilings. Okay. So. Okay. It's a bit bad on my part that it took me this long. Yeah, no memes. Our current context is just discussing hypergraph rewriting generally. And obviously we want to make progress in the infrageometry, but we're essentially just circling back to hypergraph rewriting because that is at the foundation of everything we're doing right now. So we better understand what we're doing when we do hypergraph rewriting. So okay, because this changes. This actually, the funny part is that mathematically, this vertex address kind of perspective can implement how people think of hypergraphs in set theory and mathematics in general, but it is more specific than that. In some sense, it's kind of more general but more specific at the same time. Like, because you can have you need these notions of identities on, like the rewriting rules being pattern matchings for addresses. Sorry, pattern matchings that don't care about addresses, but they care whether addresses are the same or not. Right. So when you write like if I have a rewrite rule in my screen anywhere, this is crashing, but I can't show anything Mathematica. It's completely crashed.
Just kill it. Can't you kill it?
Well, now I can. Before it was just not even clicking. Yeah, it's like a multiset. So multiset is related. So did it kill the whole thing? I think so. Yeah. Anyway. Yeah, I think. So what I was saying is that if you have rewrites like that, the vertex names are the addresses essentially, and our Packlet, whenever there are two different vertex names, they're always going to be represented as separate, distinct points in the graph, and so like they're going to be the nodes.
Well, so this also have addresses. Yeah. We did when you start doing rewriting for the multi-computation purposes.
Did you say edges? I didn't hear.
Yes, edges.
Yes, edges. Yeah. Yeah, edges need addresses, I guess, because you need multi-edges, right?
But for the causality, that's exactly the addresses that you have to track. Because if you rewrite edges, you don't rewrite like vertices.
Yeah. Yeah, that's the point. So edge addresses are in some sense almost like labels, I guess.
Just unique. Yeah.
Yeah. No, they are unique. Yeah. I mean, I guess addresses are inevitable when you want to have multi-set behavior. That's exactly what Ming was saying. It's like if you want multi-set behavior, but you actually want to distinguish between objects of the same kind. Yeah. It's basically like trying to capture what we experience in real life, right? Like you see objects that are indistinguishable to you, even though they are indistinguishable from your experience of it individually on each of them. They're still separate in space somehow, and they're like, you can operate them distinctly. And so this address system is mostly just keeping track of that sort of thing. Makes sense. No, that's okay. Yeah, I don't want to abuse next time. It means it's taking a shot in the dark. Professor Whitberger has been working on a multi-set based tree system. Yeah, this is basically what we are doing here. Anyway, Brady is commenting, couldn't you have rewrites which only care about topology and not address names? As in, this pattern goes to that pattern, but the names are irrelevant. Yeah. In fact, that's one of the questions I had for Nick, to be honest. That's basically trying to do pattern matching without regards to symmetry, which we can do. So, and in that case, you're essentially just matching topology and but you see that's kind of the interesting part. Because that's exactly right, Brady. Like you want topology to be the guiding handle when you do pattern matching, and if everything is directed, so all your edges are directed, they have full tuple structure on vertices, then that's irrelevant because there's a unique matching of a pattern. It's either a match or not a match if there exists. But when you consider something that has some degree of symmetry, either full symmetry like undirected or something cyclic or something like that, then you're going to have to account for the possible permutations. And sometimes it's not just internal symmetry of the edges, but in fact just matching symmetry, right? Like you could have the same pattern somehow permuted internally and still be a match, right? So, and there are times when that doesn't really produce two different things in terms of a topological output. If we can pattern match, is there a potential to use the 4' patterns to map the territory? What do you mean the 4' patterns? Does that speak to you, Nick? 4' patterns?
No.
Maybe memes, can you elaborate? Oh, like coloring patterns, I see. Well, the idea of prime rule, so prime pattern matching based rule, it's certainly relevant to consider. I mean, when we define these kinds of rules here, we are deliberately considering the smallest ones we can think of because we know that they are going to be prime in some sense. Like, it's unclear how big you can go and still be prime, but it's obvious that if you're writing a rule that involves only two edges or something, there's just that rule, right? Like it's not possible to compose several rules to produce the same effect, which is what we mean by prime here. All right, I see memes. Yeah. But the concept of prime is actually it's actually quite relevant. But yeah, should probably end it here. I don't think we can make much more progress right now on this. But yeah, it seems pretty clear to me that we need to be thinking about this. Okay, it's very good to hear that we were independently thinking of vertices as the same kind of address positions that are populated. I think it's natural to go there. Yeah, just in some sense, I'm kind of scared of going all the length of hypergraph symmetry rewriting because everyone I know, by everyone I mean all the people who have worked on this rewriting stuff in mathematics and all these very clever people, they failed to do a unified description or treatment of hypergraph rewriting when you can have arbitrary symmetries for your edges. So yeah, but it's a good challenge. We should be known for solving the general hypergraph symmetry. All right. So I see a few viewers that just joined recently. Sorry guys, we're at the end of the live stream. We are having a community live stream tomorrow, so do join us around the same time, a bit earlier. We're gonna talk about upcoming announcements, events. We will highlight some community contributions. We'll let you know about our workshop that is happening next week. So in case anyone wants to know more about this rewriting stuff and hear from experts, I'll share very quickly we can show it here. Yes, actually, this is the website of our event next week. I'm just going to be traveling to Paris. I'm going to host it there. So I'll just type this on chat. You guys can register if you want. So we will try to live stream. I mean, I can't confirm 100% now that there will be live streams for everything because of possible connectivity issues, but that's the intention. So in principle, every session will be live streamed. Here you can see some of the sessions. And this is in case you don't come to the community live stream tomorrow. I'm just giving you some sneak peek. So on Monday next week, a lot of ternary algebra stuff. This is sort of pure algebra. This guy, Richard Kerner, is kind of one of the leading figures in ternary non-associative stuff, especially with respect to physics. Viktor Abramov, for those of you who remember the fish product that I've presented in some of my stuff, he was the guy who computationally found the axiom, and I was the guy who noted that it was a fish. But so yeah, that happened almost 15 years ago. And then on the second day, we're gonna have a lot of hypergraph rewriting and hypergraph analysis talks. We're gonna have Francesco Lotito, actually, who is developer with Hypergraph X, which in some sense is our main competition when it comes to hypergraph computing. So it'll be nice if you want to chat with them and talk about our functions. And then on the final day, we will talk about hypermatrices proper, and I'll be showing you some Plex diagrams, and Josh will talk about the Cherry-Messner product and our research there. So yeah, just so attendance is free. We will live stream it, but if you want to actually ask questions live, just click on register here. Should be taken to a very quick form, and that's how you register for the event, and you will get the Zoom link, and you can join our session. And we will be discussing on the Discord. So, in case you want to see on the Discord here, I mean, for those of you guys who are on the Discord, you would already know that you can navigate down here. You see Hypermatrix Workshop 2024. So here's already some announcements. There'll be a channel for questions, and then each session will have its own sort of forum post and thread, so people can discuss the specifics. So yeah, in case you don't have the time tomorrow for the community live stream, that's the most important, most imminent thing that's happening next Monday. But otherwise, I'll see you on the Discord. I'll see you tomorrow in the community live stream and generally online. Thanks very much.